The next type of problem comes from physics, and let's look at the following setup. Suppose that we have the mass m0 of radioactive material with half-life T 1/2. What is a mass? Or what is the remaining mass? After time t has elapsed. Okay, so you can see immediately that this is a problem that is kind of reminiscent of the problem of the bacteria, in a sense that with the only difference that the bacteria, in the way we initially formulated the problem, the amount of bacteria was increasing. In this case, this is a radioactive material, so it decays. So the mass should be decreasing in time, but otherwise things are similar in the following sense. So number one, if we want to establish what mass at the time t is, let's actually label first. So let m of t denote the mass remaining at time t. And if we use this notation, then we know that m of 0 is going to be the initial mass that is available to you, and that's m0. So the rate of decay is going to be equal to m prime of t, right? And m prime of t, this rate of decay, will satisfy the following conditions. So condition number one, because the mass of radioactive material is always decreasing, then m prime of t must be less than 0. And number two, just like it was a case with bacteria, when the radioactive decay happens, then every component, every part of the material is decaying. So the more material you have, the larger mass is going to be lost at the unit of time. And so it doesn't take long to realize that we have the same property that we saw before for bacteria, that m prime of t must be proportional to the mass, to the remaining mass at the time t. And because we're talking about decay, the rate of decay is always negative. So either I can set k to be a negative number or k is positive. I prefer that k always stays a positive number. So then the sign I'm going to write explicitly by writing minus k. All right, and so then what we're getting is that m prime equal to minus k m is the ODE. And not just an ODE, again, if you look at it carefully, you see that this is a linear ODE. Governing radioactive decay. And if we now solve that ODE, we should recover the expression for mass at the time t. So to determine that, we need to solve the initial value problem. M prime of t is equal to minus km, and m of 0 is equal to m0. So basically exactly the same initial value problem as before for bacteria, except that now the coefficient is minus k instead of k. So let's solve, because it's a linear equation, we should be able to do it. So then I can find the integrating factor, mu of t, which is going to be, well, first of all, let's rewrite the equation in the standard form. M prime plus km equal 0. So k is your p of x in the linear equation. So mu of t is e to the power integral k dt. So this is e to the k t. So even if I'm multiplying the equation by the integrating factor, the left-hand side becomes e to the k t m quantity prime, and the right-hand side is 0. And so integrating both sides, we have e to the k t m equal to a constant. And so m of t is c e to the kt. And finally, we use the initial condition. M of 0 is supposed to be m0, but on the other hand, it is c e to the power 0, so c should be m0, and then substituting it into the solution, we're going to get m of t is m0 e to the power kt. Okay, so the rate of decay then is determined by this constant k that we don't know, but instead we know half-life. And clearly, again, half-life large means that the decay is slower. Half-life small means that the decay is faster. So half-life must be related to k in the sense that both prescribe the sense of the rate of decay. So somehow we should be able to connect m0 and connect half-life t1/2 and k, and that's let's do that now. So to relate k to t1/2, here is what we're going to do. We know that the mass after half-life is going to be 1/2 of a mass that you had in the beginning. And on the other hand, m at t of 1/2 is determined again by the expression for m of t that we figured out. So that is m0 e to the k times t1/2. So what we got is that 1/2 m naught is m naught times e to the k t 1/2. I can cancel m naught from both sides. So e to the k times t 1/2, this must be equal to 1/2. This I can rewrite as, just like we did before, e to the k to the power t 1/2 is equal to 1/2. And then taking a root, t 1/2 root of both sides, e to the k should be 1/2 to the power 1 over t 1/2. All right, so then I know e to the k, and now I can use it in my expression for m. So m of t was m naught e to the k t. I can rewrite that as m naught e to the k raised to the power t. And then e to the k is 1/2 to the power 1 over capital T 1/2, right? That's my e to the k, and that has to be raised to the power t. And then combination of powers, power to the power, that's a product of powers, so this is m naught, and then 1/2 to t over t 1/2. And this kind of makes sense. So t over t 1/2 tells you how many half-lives are going to fit into the time little t. And after each half-life, the amount of material is going to be divided by half. So if, for example, t is 3 times t 1/2, 3 half-lives have passed, and then you get 1/2 cube, so 1/8. So after 3 half-lives, you have 1/8 of the initial amount of material. And so we get the second formula for m of t, now written in terms of the initial amount and then half-life. All right, so you can use either formula in problems, in the practical problems that you're trying to solve. All right, so let's do an example. Example of this. Suppose we initially have one kilogram of radioactive material. With half-life let's say 10 days. How much of the material is left after, let's say, 12 hours. So the biggest difficulty in this problem is to relate different time scales. I have half-life, which is expressed in terms of days, and I want to figure out how much of the material is left after a certain number of hours. Also, we have to convert either everything into days or everything into hours. Let's convert into days. So 12 hours are going to be equal to 1/2 of a day. And so then what I'm looking for is m of 1/2. And really, there is not much to do because I know that m of t is given by this formula. If I am using half-life, so then I know that m of 1/2 must be equal to 1 over 2. T is 1/2, and half-life is 10. So we have 1 over 2 to the power 1 over 20. And so 2 to the power 1 over 20 actually is very close to 1, 20th root of 2. So what we get is that we, roughly speaking, have still the same amount of material than in the beginning. But the exact amount is this 1 over 2 to the power 1/20. So this problem actually is very simple because you use the second formula and that's it. Let's try a slightly different version of this. So let's say, suppose that we initially still have 1/2 kilograms of radioactive material, but let's say I don't know now what half-life is. But instead, I know the following. So suppose in addition to this, I would know that I have, let's say, 500, well, not even 500, and 300 grams are left after 1 hour. And then the same question, how much is left after 12 hours. So my choice, again, is to use two different formulas, either the formula with a half-life that we have here, or the formula with K that we have up here. And I'm going to use a formula with K because in this case half-life is not given to me, so it would be difficult to use the formula with half-life. Let's use this one. So I know that m of t is m0 e to the kt. K I don't know, but m0 I know. M0 is equal to 1 kilogram. So this is e to the kt. And also what we know, that m of 1, now my time is measured in terms of hours, m of 1 is equal to 300 grams, so mass is going to be in terms of kilograms, so 300 grams is 0.3 kilogram, and that is equal to E to the K times 1. Right, so E to the K times 1 is E to the K. Well, but if that is true, then my m of t is e to the k t, which is e to the k raised to the power t. I just found e to the k is 0.3, so this is 0.3 to the power t. Right? So we found e to the k by using the amount of material left after 1 hour. And that allows us to determine e to the k. Once I know e to the k, e to the kt is e to the k to the power t. E to the k is 0.3, so we're done with the formula. And then finally, so then the question was to figure out how much material is left after 12 hours. So m of 12 should be 0.3 to the power 12, and that should be in kilograms. So we're done. Whatever this is, 0.3 to the 12 actually is going to be a fairly small number, so that means that in this case the decay is going to happen extremely fast. Okay, in the next lecture we're going to talk about a different application, so to be discussed soon.